I'm going to tell you a little bit about the blue tide simulations that we've been running on blue waters for the last few years. So the underlying umbrella here is to study this epoch of the cosmic dawn. So this is the largely unexplored frontier of the early universe where the first galaxies and black holes are starting to form. This is like within the first billion years of since the Big Bang. This is when we see the very first formation of objects. So this is still largely an unexplored frontier. That's why we kind of like to go there. Some speakers yesterday have already spoken about this epoch of the universe that we're trying to sort of unfold the history of. What do we know? And I'm going to be talking a lot about redshift, and I'm talking about this, so when you see these big numbers with a Z, if you're not familiar with it, I'm talking within this first billion years of the cosmic history. Okay, so what do we know about this cosmic frontier from actual observations? We have a few hints. We know about actually two quasars. These are supermassive black holes that powers extremely luminous events in the universe that allow us to indeed probe this very high redshift, this very early universe in an unparalleled way, just because they're super bright. And then we know about very faint galaxies. The Hubble Space Telescope has been staring at patches of the sky deep enough to give us some glimpses of these very first galaxies. There's perhaps a few tens to a few hundreds, a few tens at most at the very, very edge of what we've been able to probe. But why do we like to go there? We kind of want to know, how does everything start? What is the first object that forms in the universe? Because it's cool, because it's fun, because we want to kind of know how does it all start, but also because it really is that, this first generation of galaxies and black holes are really setting the stage for the rest. They actually have sort of a reaction onto what the universe is doing in many ways, something that Nick told us about, reionization and so on. They influence the cosmic history from then on, and all the way to the galaxies and black holes and the universe that we see today. So we kind of want to go there. We want to understand this. And that's why there is many very large, very super expensive telescopes, the successor of Hubble, JWST, and many other missions that are going to try and look for this, go into as an explored universe and finally find millions of galaxies and even thousands of quasars and black holes in this early epoch. So we are motivated by this to then go and predict what we should be seeing, right? So it's an extreme challenge for observations to actually probe this very early universe, and is an extreme challenge also for us to understand what should be going on in this early universe. What do we expect to actually see out there? So both detecting and understanding, predicting this early epoch is a fundamental challenge for us, and a challenge that we can take on with blue tides and blue waters. Okay, so what is the challenge is that we are trying to simulate this very large universe, right, that is out there. And the first galaxies are rare events, even more so the first quasars, the first black holes. So we are trying to simulate a very large piece of universe where rare events are happening, and those rare events are what we're really after, what the interesting stuff is. So this is the kind of work that we got involved into. So this is a large-scale cosmological simulation of blue tides, and I'll just pick on a few things, right, that we've been able to do. But this is sort of actually in the background there, at this resolution, is the full volume of the simulation, is the density field, and then zooming in into this particular region, zooming in, it actually illustrates just the dynamic range of these calculations, where we have gigaparsec scales, billions of light years across this volume, but also the resolution to understand the structure of galaxies right inside. So the challenge here that we could take on with blue tides was to do these very first objects that are rare and tiny in this large volume, and just go for it and just do it. Okay, so this is where this blue tide, just to reemphasize, is a sketch of cosmic history. This is blue tides, just covers up to basically the first billion years, and actually is exciting, is actually meets up with some of the current observations within this very early universe. So I already said a few words, again, very briefly. So an overview, blue tides is run on blue water, basically pretty much on the full machine. This is the kind of the only cosmological run that has been run on the full machine, and the motivation is indeed to tackle this first, resolve the galaxies and the large-scale structure in the universe. So what do we do in this kind of simulation? Very briefly, again, so it was introduced, this sort of cosmic structure formation cosmological simulation were introduced yesterday, but we are solving for gravity. We start from an initial density field set up by the initial condition of the universe, and we evolve it. So we need to know what gravity is doing to this. This is done through a hybrid tree and PM kind of algorithm. And then we need to follow how gas falls into this potential, well, it follows the dark matter, the evolution of gravity as well, and that amounts to pretty much solving for the energy conservation equations, right? So the hydrodynamics. So this is sort of the backbone without going through it, and we want to do it in a fully cosmological context in this universe that is expanding under what we know about general relativity and Friedmann equation. Okay, so what am I telling you about is doing this with one particular piece of code that is called MP-Gadget, Massively Parallel Gadget. This is the simulation code employed for this work, and it sort of follows on the Gadget code that has been around in this field for a long time, but has been improved very significantly in many aspects of both the hydrodynamics, but also just the gravity solvers, the PM solver. A lot of was done also in the I/O because of the data sizes, but also in the short range. So standard cosmological codes that do solve for these equations, but they get upgraded significantly to scale on blue tides. In terms of the physics, okay, so we want to follow the formation of these objects. There's a lot of extra physics that we need to put in. And without going again into the details, for those of you who are not familiar, but we want to follow how basically the stars form. So gas cools into these potential wells. Maybe there's molecular gas that is very important at this early phase. There is stars form, go supernova, inject energy. We call this feedback back into the gas that is trying to form stars. We want to put in black holes as well. Okay, so there's a whole range of physics that we put in the simulations. Much of it was also described yesterday. What do we end up with is okay, this is very bright, but it doesn't matter, I'll show you more images, is indeed a universe now, a synthetic universe, right, from our simulation that now has hundreds of thousands of galaxies in this very first epoch. So we can play. You know, we have a lot of universe out at this very early redshift with galaxies that are formed, and they kind of agree pretty well, at least with what it's observed. Okay, so this is what we typically plot sort of as a validation, also can be used in different ways. Is the galaxy luminosity function. How many galaxies do we have, and what luminosity do they have? This sort of tells us have we gone right or wrong. Okay, so this is different epochs as the universe evolves this way. This is luminosity of galaxies, and they're all binned in these luminosity bins like the observers do, and the observers have these black points. Okay, so this is what we currently know from this very deep Hubble fields observations of the galaxy at this early epoch, and in blue is the prediction from blue tides. So it says, okay, we kind of got the right galaxy population statistic, at least in the range that is being observed. Okay, there are not many galaxies observed if you notice what the numbers are in here. But I've talked also last year and other times about some of the stuff that is kind of fun to look at in regions that are yet unexplored. What are the very bright galaxies that we have yet to discover, and other features of this. What I want to talk a bit more today is about the first most massive black holes, and what we predict from blue tides. So what are these objects? So these have posed a really challenging question to our structural formation model. Basically, we know that black holes power these activity of quasars. So the most luminous objects that we see in the universe are powered by supermassive black holes. The surprising fact is that some of the absolute brightest object, this is the luminosity as a function of black hole mass, are actually this super high redshift object. Okay, obviously to be seen they have to be bright. But as these are for instance, two examples here. This is the rest of the quasar population that we know more locally. These are the ones that have been observed in this super, super high redshift universe when before the universe is 1 billion years old. And their luminosity, we see them because they're so bright, implies that they have to have massive black holes powering this luminosity that has with masses of 1 billion to 10 billion solar masses. What is again surprising about these masses that when we look at black holes today, black holes leaving galaxies, we observe them in the local universe. That's 13 billion years after the ones these very early ones. So this is some sample of these black holes that we measure, and in galaxies today, the most massive galaxies today have black holes that are as massive as the ones that were formed within 1 billion solar years since the Big Bang. Okay, so these first early black holes are formed in less than 1/10 of the history of the universe, but they're just as big as the biggest ones that we know about after 30 billion years. Okay, so how does that happen? What do they signal to us? What is this? Do they signal something that is going on? How could these black holes form so fast in such a short amount of time? Okay, one very fundamental piece of information is that we see just a handful of these objects, and when you calculate how many are there, right, what is the space density of these objects are extremely rare. This is just an old image of the Sloan Digital Sky Survey, just to give you a sense, okay? Every little point that you can't even resolve with your eyes here is a galaxy, and this is the local universe, okay? But just to give you a sense, it would be like if every single point is a galaxy, the rarity of this high redshift quasar would correspond to 1 point in this whole huge volume that is probed close to the whole sky that is probed by these large surveys, okay? So this is in what we call 1 per gigaparsec, is every 100 billion light years, we have one of these objects. So they're supermassive, but they're extremely rare. Okay, so here is the record holder, actually. Something that came up was discovered just over the last 6 months. Okay, so this is the absolute frontier. The previous one was 6 years prior to this. Okay, so just to give you a sense of how difficult it is. What are we doing? We're looking actually, the observers are looking every single star that's ever been observed, kind of, because these quasars will look much like a star, and then spot the brightest one and follow up and discover that actually these are quasars. So you have to follow the full sky, basically, and eventually find one. But when you find them, they are bright. These are actually images, right? And they're not faint. And this object is at less than 700 million years after the Big Bang. Okay, this is its spectrum from which we know that it is at this redshift, and there's been actually a confirmation of this as well. Okay, so this object is so bright that implies that at this early epoch, less than 800 million years since the Big Bang, it has a black hole of close to 1 billion solar masses. So briefly, how do we even expect to get black holes in this early universe? Thanks. So they have to start somewhere. So we have to have some seed in these very early galaxies that form this black hole, and then we have to grow them. So seeds could be small if they're the remnant of the very first population of stars. These stars would be forming and dying very quickly and leaving a remnant that is roughly 100 solar masses. That's what we call a small seed in the first galaxies. Or there could be regions that have such high density gas, it collapses directly, forms a black hole, black hole seed that is more like 10 to the 4, 10 to the 5 solar masses. But regardless, and these are really interesting scenarios to explore, and they're purely theoretical, we never observed this yet, but whatever the scenario is, the ultimate challenge is to take any of these seeds and grow it to these giants that we see, like the one that at redshift 7.54. So we only have a few hundred million years to do that, to go from a few hundred solar masses to 1 billion solar masses. So how feasible is this? So again, very briefly, how do black holes, do we expect them to grow? So they have these seeds. Structure formation tells us, gravity brings things together. Galaxies will merge. If the seeds, black holes, are in galaxies, they will also merge and grow. And while they do that, they carry along gas that is swallowed and accreted onto the black hole themselves. So accretion and mergers will grow these black holes across their cosmic history. There's something else that is associated with gas accretion onto a black hole. Is just as you accrete matter, you liberate a ton of energy. That's why we see the quasars that we see. But this lot of energy liberated is coupled back to the gas that in itself is trying to accrete onto the black hole. We refer to that as black hole feedback. Okay, so lots of energy liberated back, and the black hole spews it back out into the gas, and that has some effect on its growth. It slows down the gas from being accreted. So ultimately, the challenge is that we're trying to follow the full cosmological volume because these objects are so rare. We're trying to follow across all these scales what the gas is doing from falling into the dark matter halos of these first galaxies, forming the stars in these galaxies themselves, and actually getting gas all the way very close to the black hole. So it's the huge dynamic range as big as it gets. Okay, so that's the motivation, the challenge of doing calculations require getting to rare regions, getting to galaxy scales, understanding how gas gets all the way into the very center. Okay, so large volume, high resolution, and the full hydrodynamics. And that's what we try to achieve with this blue tide simulation. Okay, so a volume that would attempt, and a resolution that would attempt to give us some view of this problem. Okay, so what's interesting is that blue tides now is the only direct simulation that probes directly the condition of these very high redshift quasars. This is a result, okay? So this is the black hole mass as a function of the stellar mass in the host galaxies. This is a population of black holes in their galaxies that form in blue tides, and here we have the only lonely, very supermassive object that has a mass that approaches very closely already at redshift 8, a few 600 million years, that of the observed quasars. So we do have them, and they're as rare as we expected them to be, okay? In this whole volume, there's one. Okay, this is sort of the environment in which it forms. So this is, again, one of these blue plots that I've been showing you. This is zooming into a region where one of these black holes actually forms, okay? It's a rare, very high-density region, and the galaxy is shown also there. So we've looked into why is that the region? Why should it be there? Okay, so, and I'm not going to talk too much about it today. I think I talked about this last year, but this was a very important theoretical question. Now that we find it, why do we find it, where we find it? Okay, so it turns out that we need to pick very high density regions, rare, they are rare, but they have to have another characteristic. They have to have very low tidal fields. They have to be regions in which there's no pull from many other or one major direction, so the gas is as unimpeded as possible. So that's something that is in our initial condition, okay? So something that we throw down because that's what the universe is like, okay? Okay, so these high redshift quasars can be formed. We can achieve in special regions of low tidal fields, in rare regions, that to sustain this incredible growth, yeah, in this as rare as it gets. So this is checked, okay? We can do that. We probe directly a condition that allows us to go from this to these giants. So I want to go back briefly to this object, okay? Now we've been able to push the simulation actually just to these redshifts. So do we have this object or something that is comparable to this observation? And it's kind of fun that we do, okay? So we just got there with our allocation now, and this is basically the full population of black holes. This is the black hole masses, this is the luminosity. Here is the observed luminosity of the quasar and the inferred mass, and this is our quasar in blue tides. So it's kind of fun that we actually have reached a luminosity of quasars that are very comparable to this observed record breaker guy at 7.54. Okay, so I'll just ask one more question that we to the simulation. So you think, okay, we've grown this black hole like crazy, right? And that's fine, but does it actually ever stop growing? What's going to happen to this object? Okay, so this is going back to a little bit this issue of black hole feedback. Is the black hole doing something to this environment? This is something that people have started to probe observationally as well, even the very, very early epochs of these first quasars. So there's evidence that there's energy being spewed out from the black hole that and winds and outflows, gas is being pushed out from the vicinity. So this is what we see a little bit in the simulation, and if you look at the middle there, maybe you just had a glimpse of some outflowing gas, and actually we can measure that. So we went around these high redshift quasars, and we saw that, in fact, this feedback, even at this early epoch, the energy that is being coupled from the black hole back into the gas is sufficient to drive these enormous winds, these enormous outflows, okay? So there's velocities of gas spewing out from the central regions all the way to outside the galaxies, up to 2,000, 3,000 kilometers a second. And this gas, you can measure directly in the simulation. This is the velocity profile. The escape velocity of this gas is here. Dark matter, this is every single particle, dark matter in this halo here. They don't escape, but gas does. You can inject enough energy, and that this gas is actually exceeding the escape velocity at any radius and is being pushed out. Okay, so what's the answer? Does it stop growing? Yes, it does. There's enough energy that is injected that this black hole is achieved the maximum mass that it would ever achieve, and now galaxies sort of being the gas is being ejected out in this black hole outflow. And one very quick comment on who is the host. Okay, this black hole lives there alone. Does it have a host galaxy? What is the host galaxy? And ultimately, what we are looking at is what do black holes do in these early epochs? Do we grow black holes first, or galaxies and black holes grow together? And we know today there's a relationship between black holes and galaxy, and the bigger the galaxy, the bigger the black hole. But does this process happen, one-to-one, or how does it happen? So we have actually made synthetic James Webb Telescope predictions for what the galaxy hosts, where does it live. We have a spectra for this, and because I'm running out of time, I'm just going to tell you that the host of it is tiny. Okay, so this black hole is expected to live in this tiny little puny galaxies. This is an image of where a similar black hole to scale lives today in the universe today. This is a giant elliptical galaxies. The same kind of black holes lives in that, this redshift. Okay, so tiny, tiny galaxies for the most giant black holes. Okay, so that's what we're expecting. So in some sense, we are saying the black hole kind of overwhelms the growth early on, and the galaxy kind of follows. Okay, so it may get there. It may get to the middle of that galaxy, but the galaxy will be growing later. Okay, so I'm running out of time. I think it's a really fun time to be this. I wish I had just more allocation to do more fun stuff, but that's it. But okay, Blue Tides makes direct contact with the data, the first galaxy and the first quasar, and it's a fun place to be now to make predictions for future. Okay, I'll stop at that. So.
Very good.